The old man built. The old man built. The old man built. The old man builds. The old man builds is broken in the head. People not seeing reality has put them in the red. Where conscious and spirituality been stricken from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Spheres of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to instead. The old man builds. The old man builds. The old man builds. The old man builds.
Hey everyone and welcome. Guys, Shawn has come back. Shawn, welcome.
It's good to be back, Nathan. I really missed you. I really missed all our wonderful participants in the chat, guys. I'm so glad that you are willing to come back and see me after this long stay. So my health was very poor, so I wasn't able to do a whole lot, but I think I have enough interesting things going on in my lab that might perk up your interest in some of the things you're working on. So I'm ready to get started when you are, Nathan.
Yeah, just so you know, Shawn, my show is your show any day of the week. You just let me know.
Appreciate that. It means a lot. Thank you so much. Right. All right. Can you see the red cone, Nathan?
Yeah, everything's good.
Awesome. So, hey guys, again, I want to thank you for joining Nathan and I as we're going to start taking a look at some of the experiments that I'm working on in my lab. One of the things that comes up a lot is how do I find the resonant frequency of a coil? And so I put this diagram together. And so basically it shows you how to connect your oscope probe, how do you connect your signal generator, and then with this setup here, and the cone here, and this is my coil, what you're looking for is this on the screen. So as you're sweeping the frequency on your signal generator, when it goes low as you're sweeping, let me try this again here. When it goes low, then high, then low, then high, that low is the resonant frequency. So it's not really much harder than that. You're just again going to connect your oscope, how it's connected here. You're going to connect your signal generator as it's connected here. You're going to then just sweep your frequencies until you see this. Now it might be subtle, but when this is at its smallest, that means you've achieved resonant frequency of your coil. And so I kind of want to just reiterate that to you. Some of you guys have already seen this before, but it comes up again and again, and it's not simple to do this. So reiterating it might jog the memory. So what am I doing in my lab? When I'm working on something, I'll have a pen in my other hand, and I'm a little bit ambidextrous, so I just scribble. I scribble and draw. I know it's kind of eerie looking, but I do these kinds of things all over my lab with geometry, with glass, with wood, and I'm always drawing and expressing myself. So you kind of might see this kind of art in the stuff that I'm working with. Now, as you know, I'm working on electrodes, and I have some top secret stuff that I'm going to keep close to the vest for now, but I can give you an overall how things are going. I found this clear crock pot bowl, and inside is a little heating element, and then I stole this little lid here from my wife's pots, which didn't make her happy. And so what I'm planning on doing is taking the PE plastic or the PP plastic, polyethylene or polypropylene, and I'm going to heat it up. And then my hope is to run a little electricity through it, let it cool down, and then I'll have an electret. So this is sort of my thinking. This is all thrift store junk. I think altogether it cost me about $6. but to kind of show you the opportunities to create a controlled environment for melting your plastics. Let's see here. This is another thing, just vibrating plastics, trying to create charge. This is some of the silly stuff I'll do. I'll throw, these are mica sheets. And the reason why I'm doing this is because mica is a positive charge and the plastic is a very negative. And so possibly I can create a very high static voltage doing strange things like this. And I'll let you know this was a complete failure, but it looks kind of cool. If I run the vibrations for a little bit, all of a sudden you'll find how charged they are. These are just plastic beads for use to stuff dolls, but after shaking them together a little bit, you can pull them right out with your fingers as they stick, just kind of like a magnetic action. I've shared this with a few friends. I bought this bag of tiny glass spheres. They're very small, about the size of the point of your pen. That's how small they are. And one of the things that's interesting about them is they're all equal in size. The glass balls. They're polished and they're kid safe. You can put them in weighted blankets or stuffed animals. But what interested me was as I was carrying this bag of them, what I noticed was the beads were jumping up onto the plastic and making certain formations, certain geometric shapes. And I thought this is fascinating because what's going on is the plastic is saying, hey, I want electrons. And the glass is saying, I want to get rid of electrons. They've been staying too long. We've been wanting to get this electron who's been only playing video games in our basement. So it's time to go. And the plastic says, I'll take them. I'll take them. And so I thought this would be interesting because if we're willing to look around us, you'll start to see that fields are everywhere. And fields, these invisible fields, are manipulating matter, as you're seeing here, because these glass balls are just jumping right out into a formation. And so that just amazed me. Here's another example of it. And again, I didn't shake this bag. I didn't do anything. I just set it down on my bench and thought, wait, what is it doing? All right, so a little bit more work on electrodes. Here I have a piece of plastic. I ran some electricity through it and I've gotten to 20,000 volts. And in fact, when it goes OL like that, that means it's 22,000 volts or higher. And so zapping this little piece of plastic, it held a charge, which is promising in my electric research. I electrically charged this sand and watch the sand just jump right up to my finger. Now I'm not connected to anything. I'm not doing anything other than walking over and putting my finger near it and watching it jump up to meet my finger in the air. So again, sand is pretty interesting stuff. I've never had this sort of ability to draw sand straight up into my finger. It's one of my goofy setups for charging things. So I'm showing you on the left how powerful the high voltage is, but having those arcs is not a good idea. I'm just kind of showing it. Excuse me. But here I'm trying to charge a piece of mica, which unfortunately didn't work as well. At a thrift store, they had a little s'mores maker. There's a little hot element in here, and you just plug it in. And I was melting plastics with it, so I was making plastic s'mores. And here it is in action, kind of shining a light there. Most of the plastics that I'm working with, they go clear when you heat them up, which is really cool stuff. And there's the s'mores. This thing actually melted into a ball and was a fire hazard, so I had to get rid of it after these few shots. But I got it at the thrift store for $1, so it wasn't that big of a loss. So this is molten plastic with a heating element. I know, not accomplishing a whole lot, but I'm just learning. Electrics are all about plastic, so I'm just delving in. So this is my workbench in my garage. It's finally getting warm enough to be in the garage. So here was that crock pot looking thing that I showed you guys earlier. And here's the heating element and everything in place. And with the plan of melting some plastics. This actually was an utter failure too, but I'm failing in the right direction. This is something I was talking to Nathan about earlier. If you've heard about it, it's called Fusible alloy. I broke a piece of it and put it in this little cupcake pan, and it turned to liquid. And it's really cool stuff if you need metal in a pinch, because they're relatively cheap. I'm breaking off a piece here. I'm melting on, this is a pancake grill, so it's only like 250 degrees and it's completely liquefied. Here's how you can see the liquefying process. Now, I know you're probably saying, well, why do I care about melted metal? Well, you don't need a kiln or furnace. You don't have to buy dangerous mercury, very dangerous. You can work with liquid metal here, and it's relatively safe to work with. I poured some of it in this plastic container, that liquid, and you can still see it jiggling. Now the temperature is so low to melt this metal that it doesn't even warp the plastic I put it in. But as this metal dries, see, the crystalline structure forms in the front, which is because it has bismuth in it, and then it has a mirror shine on the back. So it's worth looking up. Fusible alloys are cheap, a lot cheaper because they mix very inexpensive metals in it. So part of it's bismuth, but it also has a bunch of other less expensive metals in it, and therefore it becomes a good option if you're looking to make metal formed parts that you don't need to have a whole lot of strength. Or if you want to make, I'm looking to make capacitors. So I'd like to have a plate that sits on top of a dielectric material. And if you put a liquid metal on that dielectric material, it'll actually then create the closest you can to the dielectric material, the metal, and that'll increase your capacitance. So that was my original thinking for playing around with these, is to make some super capacitors. All right, so if you guys remember Humpy, the 3 wire gauge coil, the top is 34 gauge, the middle is 33 gauge, the bottom is 32 gauge, and they all have equal counts of grooves. They all have equal number of turns of wire. Probably the red probably has a little bit more because it's thinner. But the reason why I'm bringing Humpy back up, because I want to start talking about some of the other experiments that I have with plasma. So some of this is going to be review. So here we have short stack, and you guys all remember short stack. And the reason why I'm going to be showing you guys this plasma discharge is to sort of get it back into your head. What is the average plasma discharge that we're all used to from my experiments? Because when I start going to the other materials, you'll start seeing that there's a difference. So short stack really carries a punch. These arcs are probably about 10 inches in length and maybe more, which puts them almost in the million volt range. And so pretty cool for a little 5-inch coil, 6-inch coil. But again, I just want everybody to sort of get this in their head. Okay, this is Shawn's same old plasma that he has. And then I kind of like to do the, let's see here, the kind of step walkthrough too. So we can kind of see the geometry slide by slide. Okay, so one of the things about this, I don't want to call it plain plasma, but more of the plasma that you've seen in the past, is it has these kinds of twisting structures. And what you'll find out is that it's not always a bouquet of plasma. It's more of, see, that's a very thin plasma, and that's going to the left. and then that's going straight up. But if you mix all of these, that's a nice, perfect backwards L. It forms that beautiful, I guess the word's bouquet again, where it looks like it's full. Doesn't look like it's just shooting one direction, then shooting in another, making an L. It's because it's moving so fast, it gives you this sort of effect. And I don't know about you guys, but I never get tired of playing with plasma. It's just such fun. All right, so more now. So that was short stack. Now I'm going to use the same setup for Humpy. This is Humpy because it has all those bumps on it. When I coated it in epoxy, you immediately know that it has sort of a skeletal frame to it. Now I'm adding voltage to it. So in adding voltage to it, this should be increasing, but it doesn't do that with Humpy with its 3 different gauges. It still stays this kind of thin, splintery shape. And then as I'm adding voltage, you'll notice that it starts flickering. It's almost as if it has an interrupter. And then the lightning bolts are more similar to what you guys would see with other Tesla coils that have an interrupter. And so I'm not sure why it's interrupting itself like this, but it's definitely different than all the plasma from the spheres and everything that I've shared since, excuse me, is this guy is, I guess you can't see, oh, and this was what we discovered last time. So this is all refresher for some of you guys. I remember now. It's DC, AC, okay, it's DC, wow, that's AC. That's so it's refreshing my memory, guys. So thank you for these are old slides. Some of them are new, I promise. Right. Okay, this is Humpy again. And I think I'm just reiterating again how it's the flicker and also that the lightning is very white and it doesn't have as many of the twirls in it, the twists and turns. And so this seems to be very unique. And so if you compared it to short stack, which just had a one consistent gauge wire, and then you compare it to this 3 gauge wire, you immediately see that the plasmas are different. And the plasma probably has its own reasons for these characteristics. It'd be probably worth maybe researching that sometime, but I find this very fascinating. The only thing that I'm really going to do different here is I've only been giving you AC, but I'm going to start giving you guys some DC. So we haven't really seen some DC. So this is the silver coil we're going to look at here on the right. That was Humpy and short stacks copper coil, but the silver wire needed a very low number of turns for the copper pipe, and it needed to have this sort of design. So the silver required much less of copper piping than Humpy and short stack. So I forget the name of my silver coil, but we're gonna look at the silver coil and as well. So this is Humpy again. And so this time, this is DC. So now I'm trying to get Humpy to do DC. And again, it's not your normal fluffy ball that we're used to like that. That looks like DC right there. But it has this sort of sharper lines inside of the fluffy ball of the plasma. And so this is different. This is very different than the other DC. And you'll see it keep shutting down. And what's happening, and I don't quite get it, but as I'm adding voltage, it just shuts down and then it goes back to a smaller, and then it builds up again, then shuts down. And I don't know why that behavior is there. It has to be linked maybe to the 3 different gauges of wire. And so here again, we're going to go DC to Humpy again. This time I got it a little better tuned. But as I've said before, this isn't your normal DC. It looks like AC inside, and yet it's of course has the fluffy outside, and it's not as the streamers aren't as long and going out as far, but it definitely has its own appearance for DC. So I'm going to kind of just step us through here because, again, can I do this? There we go. We can kind of see the DC and how it's outputting the plasma. And when I say DC, I mean a very smooth DC input. And then it's basically hitting the ZVS circuit, and then the ZVS circuit oscillates. And so it's really a smooth alternating output. And so it creates this sort of very smooth, if you can see here, the plasma is even smooth. The other sharp, jagged tendrils, if you will, that's the AC that's turned into a bumpy DC. And so this is fascinating because I've not seen Humpy or even any coil put out DC like this. This is a whole new kind of DC. It's a DC that probably warrants some more investigation. And if you look at this little dark hole here, Joe would point that out. That's a null point. And I'm starting to see these null points ever since he pointed them out. So there's one, there's one, and I think that one might be forming. So pretty interesting. But this plasma is just beautiful, and it's blurry and it's blended, and I love it when I make a new discovery like this, because you're not really seeing this kind of plasma at any other place. Not to say I'm not trying to toot my horn. This is just something that is beautiful to me. And so I wanted to share this with you guys, that 3 gauges of wire gives you a very different voltage output, or a plasma output, than you would expect. There it is at its own speed. So pretty fascinating. Also, too, when I put in DC, I have to put in more amps. For some reason, I need less amps with the AC than I do with the DC. I think this is Humpy again. I think we've seen enough, unless I do some really big close-ups here. No, it's pretty much the same. And this is me super zooming in, and kind of, let's see here. Just wanted to see if I can stop it here. I wanted to see this one because the cameras are like 1 inch away from the sparks, so I kind of wanted to take a look myself and see. It's definitely much brighter when you get close to it, so that's something I noticed. And it's definitely a lot more blended, and so here's what it looks like when I turn the light on. Kind of give you scale of where I'm running my experiments. All right, so I charged a piece of plastic, which is sort of the essential quality of an electret. I take my electrostatic meter and I set it upside down. Here's another really cool electrostatic meter. This is my favorite meter, actually. And I could bring up the plastic that I charged, and I can see it, how far. I have one plastic disc that I charged that can light up this meter about 2 feet away. So this meter is probably a must if you want to have a sensitive meter to tell you where all your fields are and their polarity, because this is a fine-tuned piece of test equipment. I bought it off Amazon. I think it was made in the UK or made in the USA, so not very cheap, but it's been a necessity for my field detection. Now, if you'll notice the glass here in this orange bowl, that the glass beads are moving, and you'll notice my hand is moving a piece of tire rubber. And as I'm moving that piece of tire rubber through on the other side of the plastic bowl, like a magnet in iron shavings, I'm manipulating the glass. And this is something I never would have expected. Excuse me, sorry. Sorry about that. You wouldn't expect that you could take a piece of rubber on the outside and make glass run up the wall. And so this is a whole different kind of magnetism, if you will. And it's pretty awesome stuff. I thought I'd share because I don't know if you guys have ever done something like this. I haven't, because I didn't know you could do this. Because what's happening here is there's fields interacting that are going right through this plastic bowl, the orange bowl. And the glasses seems to just be focused on that piece of rubber. I think I do a little bit more with it. Again, there we go. And there goes the glass. So, I mean, magnets eat your heart out. This thing's pretty cool. Another thing too is these glass spheres kind of like to take on their own formations. And the reason why the glass spheres, when they form, they don't touch each other is because they're all the same polarity. And you know that like fields repel and opposite fields attract. So the glass beads want to climb up the wall, but they don't want to be near each other as they climb up the wall. It's sort of like when the in-laws come over, you know, you don't mind if they come over, you just don't want them to get near you. No, I'm just kidding. So yeah, look at that. And the glass spheres literally leap from the bottom of the orange bowl and find their position uh, based upon a piece of black rubber behind the orange bowl. So interesting phenomenon. I've just grown a real interest in this side now of electricity, where it's sort of neglected field. Not a lot of people know this, but watching these little glass beads just fly into formation is just astounding. And by the way, I'm not doing anything behind it this time. I just swept the outside of the bowl once with the tire rubber, and that's it. Boom, and they all started jumping. There's another beautiful way. For some reason here, there's a repulsion going on. So every time I bring the rubber close to it now, they get repulsed. And so I thought that was interesting too, because they're not just attracted, but they're now repulsed. So that action is fascinating to me. And I think it'll get a little bit better in this next one. No, that was the last one. I thought, let me see if this is the one. So wherever the rubber goes, the plastic runs away. I'm sorry, the glass runs away. So wherever the rubber goes, the glass runs away. And that's what you're seeing here. So the rubber is over here, and then when the rubber sweeps, they all run away. So cool stuff. So when people ask me, so what did you do today? I rubbed an orange bowl and watched glass beads dance. Now, if you guys remember that facial zapper for your skin and for your hair that Nathan did a demonstration of, I had tried to convert it here into a power supply. And so what I did is I took the innards out, put it in this little kid's clear toy case, and then I plugged it in and I made a jack here so I can use it for high voltage. And I don't recommend it. So here I'm fiddling around with these glass spheres. I'm weighing them. I'm seeing if I can charge them. Everything, it has to be precise. There's a lot of work that goes into behind the scenes to get the stuff to do what I'm doing. It's not what you would think to get there. So here are some beads, and they're not showing a charge. Makes sense because they haven't been charged yet. And same thing. So these are all getting ready to get into the experiments to be charged. So again, just playing around with the beads to have electricity run through them. This is one of the things I did is I put a glass petri dish. If you remember that little power supply I made, that power supply is powering this little sphere down here is the positive, and then at the bottom is the negative. So here I'm going to start running some tests. So you can see here that the beads, the glass beads are having an effect where once they're charged, it pushes the electric or the plasma into this sort of design, if you will, this sort of rotating design. So I'm not sure, because if you were to just electrocute the desk or anything else, it wouldn't have this effect. There's something about the glass being positively charged and then the electrode being positively charged. There's sort of this repulsion action going on, and it's only releasing itself by the bottom plate here that is negative. So, and by the way, this is another failure of charging particles, but it's a fun failure. This is what it looks like in the dark. It just sort of has this beautiful artistic flow. You just see electrons being given to the glass, or it's being taken away from the glass, and it's forming this sort of almost, maybe stop it. We're getting some kind of shape here going on. Let's see here. I'm trying to anticipate something that Joe would say. Hey, look at this. So let's see if we can get a pattern here going. Yeah, it has definitely has a pattern. It forms these circles. Not all the time, but there we go. It's got a couple ovals. There's some more ovals. So I wonder what these shapes would be compared to something else in nature. This one almost looks like a spiral galaxy. So fascinating stuff. There's a nice bow tie. All right. Let's see. So if you'll notice, I bought all of these cheap at the thrift store plastic cups. It's a plastic wine glass inside of a plastic cup. And they're great because I get to insulate myself from these high voltages that I'm working with. Now, instead of the glass petri dish with the glass beads, this is a metal petri dish. And so this is the effect that it has when the glass is in a metal dish instead of a plastic or glass dish. So there is a noticeable difference in how the glass interacts with the charge based upon the surrounding metal. I think this is glass. I think one of the other ones was plastic. So this is glass. And I think, sorry, I think something's happening here. I think I changed the polarity. So you'll notice the glass gets really sort of stilted and they all kind of lock together. And it's kind of difficult to see. So I'll play it one more time. There you go. You see it. And you start to see the glass make these sort of shapes and they line themselves up. And it's almost as if they're lining themselves up to the field that's coming off the sphere. Here's a close up. So you're seeing that once a glass bead charges, it runs at it. Maybe it gets the electron it wanted and then jumps back. But you can see that this sphere, and by the way, this sphere is putting out about 25,000 volts, and it's AC. It's not DC. It should be DC, but I'm learning. I think this is where I put copper at the bottom. So it kind of has its own discharge sort of shape. Let's see here. Yeah, it just sort of climbs. And I think that has to do with the glass and the copper. You can kind of get a look at my setup here. And there's a close-up with the copper under it. And the beads just sort of, they're like little ants. They move around and then they stop. This stuff just fascinated me because I'm putting a lot into it. Now, this shocked me. And the beads are jumping. So I'm turning around, it's zapping me. So there's a lot of charge in here. And they're just trying to jump ship. You can see the glass spheres all outside the container. And that's just because I'm moving my hand across them. And it's still shocking me. So interesting stuff. All right, there's some stuff I had on the pyramid. So I hope you can be patient. I apologize for the repeat materials. But I think I was able to get some DC out of it. And so I had thrown all of the pyramid slides into a kind of a bowl here in hopes to have have DC. This is one thing I didn't have in my last presentation. Do you see that I have a level? Whenever you're using the rotisserie to put epoxy on your coils after winding them, you want to hot glue them, and then you want to make sure that they're level. And so before I turn on the rotisserie and add epoxy, I make sure that they're level. That's very important. You would think that that would be obvious, but it's actually not. I think that's the reason why I had Humpy. He had all those irregularities. And so I just basically pack it on and then I wait. And because it's the perfect speed, it keeps a very thick coating. And you don't have to worry about it. So there it is. Beautiful coating. I know I've shared this with some of you guys, so I apologize for the repeat material. There's the silver coil. And this one, I just packed as much 32 gauge as I could. And I call that milk and honey coil. And milk and honey has Ian's name on it. I was going to send it to him. There's another close up. Guys, I just can't get enough of how artful these coils can look. Though the pyramid has been the toughest thing I've worked with so far, I'll tell you what, it's a tough coil. There's a silver coil. Got a little bit messed up on one side because I grabbed it early. Should have waited. And let's see here. So when I first shown this, and this was the coil one, that pancake coil that didn't work. We noticed that it had these lines on my camera. And even though you're not getting a lot of discharge that's visible, it had a very strong field that was affecting the camera. And so I wanted to talk about this again because this doesn't happen when I have really good plasma coming out. This is 60, 70 volts, the total maximum. You're getting almost no discharge. And look at what it's doing to my camera. So there's something going on inside the pyramid when it's inefficient, that it projects more waves than when it's efficient. Now that seems counterintuitive, but that's what I'm discovering, is that when it's super inefficient and I'm putting all my volts and amps that I can, and I'm also about to burn things up, I get a puny discharge, but I get these incredible output waves. It's projecting its field quite far. I can't bring my camera close as I normally do because it would literally start zooming out or going to slow motion. It was basically operating my camera. Now, it's important to note that this action does not hurt my phone if it's the plasma that you saw earlier. But when it's that plasma you saw, that's when it becomes a transmitter, at least a better transmitter. Here I shared with you guys, tried different geometries of coil one. None of them worked. So this is kind of old news as well. This was the pancake that I shared with you guys, about 7,000 turns of wire. I tried to make it into a bifilar. It is a bifilar. And then I thought, well, why don't I make the bifilar coil one and then the coil two, the pyramid? But it was a failure. And so I have some 12 gauge wire, kind of show you how I build. And you guys have seen this. Some of you guys have seen this. But I'm going to build a conical or concaved coil one for the pyramid. And so this is how I did it. I just put in 3 terminal blocks like this, and then I just start pulling them apart, and I get the shape that I want. And it's not complicated. It's not hard. Now it doesn't look that great. It's not super pretty, but this was the only way I could get the pyramid to give up some of her secrets. So everything else I tried, the pyramid was very obstinate. So now I want to make sure that I put the pyramid in it. Look at that, almost perfect. Again, I hope I have some DC here for you guys, because I know I've shared AC. So let's see here. Just getting ready to test it. So you can see there on the bottom, that is a perfect example of just not having your setup balanced. There's just a slight asymmetry, and it should all be equal, but it's a little closer on this bottom side. So as I start to add voltage and current, you'll see it down there, and that will eat a hole through the pyramid if I don't deal with it. And the fix is really easy. I just sort of pull this back about a millimeter and turn it a little bit, and then boom, it's balanced and it's fine. I'm just kind of sharing these tips because if you guys are building these things and you're wondering why am I burning my coils up, just fine tune it by turning things around a little bit here, a little bit there. So this is DC. So one of the things that I probably should have done is shorten the lead, but this is DC, and it definitely has a different look. And you can even see that what's coming off the side of it has also that deep blue. So it's a fuzzy DC that we're used to, but it has its own flare. And so I'm just show it one more time. If I cut this electrode shorter, it would be more of a fluffy ball. But what's unique to the pyramid is that it does seem to keep throwing out the longer streamers like AC input. So that's one thing to notice. Also, too, the discharges on the bottom, they sort of have that deep blue. They don't have the yellow and the white that we're used to. So the wire that's surrounding it is getting hit, but it's getting hit with blue light because that's the DC. If we run the same experiment with AC, there you go. So here's the AC. And what you'll notice now is when the AC hits the bar, it's yellow. So DC hits lower on the pyramid and it's blue. And the AC hits higher and it's yellow. So I'm not sure why that is, but I thought it would be interesting to point out. Again, it's surrounded by a coil of wire, and yet when it interacts it with AC, it's yellow, and when it's DC, it's blue. Here's my setup again. I do this back and forth so you can kind of see my messy lab. So let's see here. We can now tell if it's AC or DC. Oh, it's AC because it's yellow. So that's something very unique to the pyramid. I have no other coil that acts this way. It's the pyramid that the yellow comes out from the top, and then in DC, the blue comes out from the bottom. So that's something worth maybe investigating further, because it is an interesting phenomenon. And I'm not sure why that is. You would think that AC being more powerful, it might go through all of the pyramid, but nope, it tends to come to the top, and then DC comes out the bottom. I think this is one more. I think this is the top shot. I think you guys have seen this before, but if there's some new guys that are seeing it, I think this is one of the prettier displays. I think so. I think this is going to be a top view. I'm going to crank it, get it up to the max voltage. It's pretty fascinating because this pyramid is it's so small and it fits in this large bowl. The bowl is about 2 inches, extends 2 inches higher than the pyramid. And you could run no other Tesla coil like this. And I don't know why, but it seems that almost like a reverse cone that's needed, and the pyramid has to be below inside this sort of conical, um, what else? Vortex shaped, sort of vortex shape here. It has to be set deep in the vortex shape in order for it to produce plasma. So I kind of learned that trial and error and a few gray hairs, and I was able to get it to work. Let's see, this is not unique. We'll go switch to something more interesting. Is this DC again? No, it's not DC. I think this was a straight top shot. You're gonna see a lot of yellow. Interesting. We'll get past this one. There's the beautiful capacitor bank that Ian made me. Tell you what, I get these experiments looking awesome because of his help. You can see that the pyramid's very low in the vortex shape. This was the only way I could get this pyramid to give up its secrets. So pretty interesting. There's another side view. All right, so Bernie mentioned in my last presentation, oh boy, a month ago maybe, that maybe there's some transmutation going on when the plasma hits the side railing. So what I thought I'd do is I thought I'd put a piece of copper on the side there, and now I'm out of order. Sorry about that. Out of order. I'll get to the part. Oh man. Okay. We'll see. All right, this is the silver coil. There's a guy by the name Bob Greenier. He was evidently using some still shots of my silver coil. So I'm honored, I'm humbled that somebody as smart and talented as him, that he'd be interested in some of my work. So I was overwhelmed when I heard the news that his part of his presentation was the plasma coming from my silver coil, 99.9% silver magnet wire, 33.5 gauge or 34.5 gauge, some weird size. And it probably has about 2,000 or 3,000 turns of wire on a 4-inch coil. There she is again, the silver coil. Put a lot of hot glue because I didn't want to epoxy it again. And I want so if you use the hot glue from the hot glue gun, it's like a quick fix. Otherwise, you're going to leak plasma everywhere. And I only want plasma coming out of the point, so that's where I just put the glue gun, and that way then the pressure goes straight up instead of out the sides and stuff. And so this is a close-up of the silver coil. I don't know if I had this last time, but the silver coil definitely has its own shape. The output are very straight. There's no sort of bends. These things are coming out straight shots, which is fascinating. Also, too, we can't hear the sound here, but this silver coil, it sounds like butter. It sounds like a light rain on a warm spring day. It's peaceful. That's all. The only way I can explain it is it just has this sort of rainy day kind of comfort, almost like those white noise machines you buy, and they have the sounds of weather. Okay, I think I've already showed you guys that. Let's see here. Thanks for hanging in there, guys. We're getting there. All right, so this is DC with the silver coils. This is something I haven't shared yet. Now, the silver definitely puts out a really nice, almost a sphere, probably more egg-shaped an oblong fluff of, it's very symmetrical. It's definitely very different. It has a lot more yellow in the center than what you would expect on other DC. Let's see here. I think I blew the breaker here. Let's see here. I can do this again. There we go. So yeah, this really was fun to get this to be pure DC. And I kind of want to do what we did last time, is kind of walk through it so you can see if we can see any differences in this plasma than others. Has a lot of yellow. Again, that's I always see that yellow grow when I add current, but I never see yellow on this scale. So this is definitely a silver thing. This silver is making almost, I'd say, a quarter of this that pure yellow plasma. So that's very cool, very interesting, very new, and you're seeing a lot of the null zones too, which you're seeing here. But yeah, this is like a gentle plasma. It's not imposing. It's not jagged. It's almost calming when you see it. And again, that yellow only appears in the silver. Normally, yellow is just a little tiny dot at the end of the wire, but not with the silver. So cool stuff to see how different materials act differently with plasma. All of getting DC to work on these was a challenge for me. None of this was easy for me, because I had the 3-wire, I had the silver, and I had the pyramid. So those are all completely new coils to me. So we're almost done here, guys. So this is having fun with the glass beads. This is a clear plastic bowl. And I do a slow motion here because I want you to see how the glass balls roll, these polished spheres roll on a plastic bowl, and it looks like normal. Nothing out of the ordinary here. I mean, this is what you would expect. Now, I'm going to add that tire rubber to the back, and then I'm going to start shaking it. And you immediately saw when I picked it up that it started forming these sort of its own little groupings of glass. And so I thought, it looks like there's some activity of fields or something going on in this, but you can see that adding that little tire rubber to the back, it immediately changed the shape of the fields that these glass spheres are interacting with, and so you're getting this sort of design. So I decided to do this in slow motion to maybe we can get some hints into what's really going on. And I don't know if I got hints, but when you see that the tire rubber is really close, where it shows darker, it seemed like that's where the glass is sticking to the most. But that theory kind of doesn't work at all at every time. But I thought it'd be worth seeing that. Okay, I have a clear plastic bowl, nothing. The glass spins around. If I put a rubber under it, now this plastic bowl is thick. It's probably an 1/8 inch thick, but a little piece of rubber under it, and all of a sudden the glass takes on um, its own shape as it interacts and builds strong fields. And so this is what I've been doing while I haven't been feeling good, and just again trying to see how I can discover and work with all the fields that surround us every day. And so this is just one of those experiments, something elegant, something soothing about how glass and these fields work together. It's just fascinating. Let's see here. Okay, I don't know what I did here. Sorry, I'm not hitting anything here. Okay, so here I use the clear bowl so you can actually see the tire rubber. So what I'm doing is I'm just sort of going back and forth, And as I go back and forth, I'm starting to charge the glass. But this time, this is what I tried to show you earlier. This is the repulsion. So there'll be a group of glass hanging out. Here you go. You can see them, and they'll run. They'll run right from it. See how it just broke away? So that's different. Why isn't it attractive? Why is it all running now? There's some sort of repulsion thing going on. And I don't get it because it's a piece of rubber. It doesn't have a positive and a negative side. It's just rubber. And it's just glass. So here I am. I'm kind of showing it again. And it's just as I move it. Oh, so I did a slow-mo here because I wanted to see how when it comes close to the glass runs. Now it's staying on the vertical side of the bowl, okay? So those glass beads have quite a bit of charge to stick. But when that rubber comes, instead of it making glass fields, it's scaring them away. And so again, this fascinated me. Why is the tire rubber scaring the glass through a plastic bowl? And so I kind of leave it here because it wants to run. It's not running anymore. So something's going on with the polarities. It's starting to break up. So fun stuff. And that is it. That's the end of my presentation. Right. Thank you guys for listening. Thank you guys. I appreciate it. I look forward to your questions.
All right, Shawn. That's just cool, by the way. It might be the friction right there. Friction's causing all the motion for it to attract or repel.
Yeah, it's scraping off charge and putting it in different polarities. And you see the people put a magnet under the table and they make the stuff move, but have you ever put a piece of rubber under a table and made an insulator move? I hadn't heard of that. It's something new, but it's kind of showing the power of fields that surround us.
Cool.
What
Yeah, there was a couple. Go ahead.
All right.
Oh, go ahead.
What did you think of the DC, the shapes of the DC for, let's say, the silver and the pyramid and for Humpy?
Okay, the silver was awesome, by the way. Big and fluffy, like an egg, not so much a round circle, but it was awesome.
Yeah.
See, that discharge out of that pyramid is absolutely insane.
Yeah.
It almost looks like you could raise that number one coil a little higher and still get it to discharge just fine.
Right. Right. Which is non-intuitive. If you built enough Tesla coils, that's just an interaction that you would have to just wouldn't guess, I guess, the first time.
Yeah, but if you look at the Pyramid of Egypt, if you think about it and you're pulling in a vortex to it, it makes all the sense in the world why that coil would be higher to get the vortex to pull into it. Just changes your thinking about how it works.
Right, right.
It's a little different.
What about the DC in the pyramid versus the AC? Remember the DC on the pyramid had the lightning bolts that were low on the pyramid and they were thick blue? Whereas
and then you get the yellow.
Yeah, and then the AC was on the top and it was yellow. What are your thoughts on that?
I don't know, Shawn. That's something you'd have to have in your lab in front of you, man. That's something only you can answer. But it looked wild. I mean, I really enjoyed it.
Awesome. Oh, it's good to see the gang. Hey, guys. Good to see you, Crypto. Oh, Jar Jar, I see you. Ulysses, QUO, DTN, good to see you. John Bigman, Negres, Coils, Johnny Yuma. Joe, good to see you, Joe. Yeah, we got some good people here. They're all good people. Lots of questions. I guess I have to give a shout out. I just sort of touched on what I'm doing with electrics. Jar Jar and I we're working on them together. Jarvis, Brent Jarvis, Mr. Lanius. So there are some trade secrets that we're having, but I thought I'd give you guys a taste of the invisible fields and how they can really form geometries around us with just almost minimal effort. You didn't see me really working for getting that glass to climb the bowl. Um, and so it's just fascinating stuff. And when I first set that bag of glass spheres down on the ground and they started climbing up the plastic, I immediately saw something with potential. And I wonder if that's something that we, in our busy lives, we miss things like that. I mean, I wonder if the people who sell that glass and just load it up and have they ever seen it? And I don't
Oh, I'm
want to
sure
pick
they
on
have.
them. What's that?
I'm sure they have. I bet you could probably find something online about the factories about them, and I
Uh-huh.
might show you what they're saying about it.
Mm,
That'd be an interesting watch.
yeah, interesting. Thank you, Nedge Coils. I appreciate that. I'm glad you guys like my coils. I hope you guys learned something or at least see something interesting. I appreciate all the kind words. Um, yeah, so
There's some questions on here for you, Shawn.
mhm.
Can you cast silicone molds too? This goes back to when you first started and you were talking about the casting material.
So I guess you could. I mean, there are silicone, even caulks you can buy that you can just inject into a mold. So I bet you can do that. One of the plastics I thought I had that I didn't show, it's called a polymorph, and it's a kid's um, it's like a kid's toy plastic. I'm gonna pull it up real quick while we're talking because I think that
Yeah,
it's
go
gonna
for it.
be interesting. And I felt like that if you don't own a 3D printer, then this is really the poor man's 3D printer. And I think that, and I don't want to put that down because there are shapes that I can't build that I want to build. And so with this polymorph stuff, um, you can do anything you want. It's a safe plastic. Um, here we go. Here we go. Let's pull up here. So polymorph is just a brand. Okay, polymorph it's actually the plastic's called PCL. And so I'm going to share my screen. Let's see here, share my window actually. All right, let me know when you can see it, Nathan.
Yeah, it's right there.
All right, so this is what I'm speaking about. If you put these little pellets in some hot water, just literally make some hot water for tea, put this in here, it'll run clear, and then you can pull it out and it stays moldable for probably a couple minutes. But once it's molded, it's a hard plastic. It's when I say hard, it's like a hard nylon plastic. It's a hard but a flexible plastic. And then if you say, hey, you know what, I don't like that shape, you just put your form, your design, whatever you made with it, put it back in that hot cup of water,
Mhm.
turns clear. You can use it over and over and over again. You can eat off of it. It's kid safe, food safe. But it surprised me that when you molded it and it cooled, that it was a useful plastic. It wasn't just this little Play-Doh game. No, this was literally a plastic that you can create, let's say, a part you need, a little tiny plastic part you need. You could create it with this and it would be durable. And so now I didn't buy that for that reason. I bought it because I thought I wanted to maybe electrocute it and see if I can charge it. But as I started playing with it, I thought, oh my goodness, the poor man's 3D printer. Make anything out of this plastic. So I thought I'd share it. You can get it cheaper than this. I'm just kind of bringing up the first that came up in my search. So what do you think, Nathan?
Oh, dude, it's awesome. It's like Play-Doh that hardens out to be, you know what I mean, the shape you want. It's
Yeah,
perfect.
it's perfect.
Yeah. Just so they know in the chat, they kept saying glass. This isn't the glass beads he was talking about. This is something totally different.
Okay, yes, yes. The glass beads are pure polished glass, and they remove all of any dust, anything from it, because it's kid safe. You put it in dolls, put it in blankets. So that's the glass spheres. Those are just pellets that you can use in hot water. And so my thinking was, you have metal that heats up at like 200 degrees, and then you have a hard plastic that melts at like 140 degrees. And now I can form metal and plastic, and there's a purpose that I mean, there are things I can think about that I want to do with that right away. My first thought was I want to make capacitors because I can just form my own plate, form my own dielectric, shape, size, and yeah, so pretty exciting. That was the biggest things I wanted to share with you guys. Were those two things.
Okay, I got another question here for you, Shawn, or more of a statement.
Mhm.
You're probably overheating your transistor. It develops a crack when that opens, and it closes down and starts conducting again. So this is when your coil was running, and then it stopped, restarted, and then continued again.
Yeah, that's an interesting theory. Thank you for sharing, Anthony. So there's something, and that might be true. I'll have to look into that. But there are different resonant frequencies, and there are certain drops between them. So when you saw my spark get big and then it went to little, that's I was changing the capacitance real quick. So I'd flip a switch and it would add 40 nanofarads right away. I'd flip a switch, add 40 nanometers, and so it caused it to go big, big, big. I flipped that last switch, that means it was out of resonance, and then it would drop down. And because I was running a lot of current through it, it was flipping that little breaker. So it was a kind of a combination of adding capacitance, and it flipping the breaker. But the cracks in the transistor, I mean, I'm going to test that. Because now that I never design a circuit where I can't swap out the transistors or the MOSFETs. Always unloose 3 screws, pop it out, put a new one in, we're good to go. So I'll try that next time. So thanks for sharing, Anthony.
Society High Science asked on lumpy, I believe it is. There's 3 wire gauges.
Yes. So there are 3 wire gauges, 34, 33, and 32. And they're magnet wire. And I gave them each the same number of grooves that I wound them in. And then I tried to wind them as the same windings, but not quite, because 34 is thinner than 32. So I kind of focused on getting them to be equal. So there's some more turns on the 34 than there is on the 32. So my concern was is if I did the same number of turns for each, I would have ended up winding a cone. Because as you go thinner wire, it's gonna be more take less space. So yeah, those are the gauges, and those are my 3 gauges, my favorite 3 gauges of wire. I don't really go for other gauges. I know I bought some 30 gauge, but I'm kind of scared to use it, and because I get such good reaction, good quality plasma from 32, 33, and 34. So what do you think, Nathan?
Well, it kind of falls in the middle there, right? I mean, I've used 28 gauge and I get beautiful plasma out of it. No problem at all.
That's
I haven't used 30. I was planning to use 30. You know what I mean? I had a mishap with a coil or wire this week and destroyed it in shipping. So
I saw
I was
that, yeah.
gonna have a bunch of beautiful coils out of it, and now I have nothing. So it sucks.
Yeah,
But yeah, I mean, look, it's all about the resonance, so I don't think it matters.
I think you're right. And I think we have different giftings, because you can make thick wire sing. I have a box full of 28 gauge, 23 gauge Tesla coils. It's a whole graveyard. I wrote on the outside of the box of shame.
Nice. Dude, I got coiled behind me, Shawn. You see the tallest one?
Yeah, the red tall one.
That's 28 gauge. The one right next to it, the shortest one,
Mm-hmm.
that's 32 gauge. You can see the difference, but they're the same capacity. So
Oh wow.
yeah, it just
Cool.
changes the you know, what I mean, amount of wire you have to use to get the same thing.
Yeah.
So
Incredible. Have you gotten sparks out of the 23 gauge?
the 23 gauge, I haven't tried it out of the 23. The 28
Oh,
gauge,
28.
yes.
Sorry, you got it out of 28. Is
Yeah,
that
that one's in 28. I got a green one in 26 gauge, and I bet you I can rip that sucker hard. I haven't hooked it up to AC yet, though.
was that the one that I sent you the Java TC for?
No, I don't think so.
No,
No, no, no.
the 1 megahertz one that we worked on.
Oh yeah. No, yes. Sorry, I'm
No worries.
lost my mind on Java. Charlie C wanted those coils, man, and I sent them to him. 1 megahertz Tesla coils. So
Nice. That's cool. All right, let's check out the chat.
yeah, there's a lot going on in the chat, man. When you're running different coils in there, man, everybody loves that plasma.
Thank you. John Bigman says, wait, save that video, man. That is the most interesting video I've seen. I appreciate that. I really do, John. Thank you. Very cool. Let's see. Johnny Yuma says, I'm going to leave this static electricity and go to beneficence. Best of luck. Thanks, man.
Dude, I think he was trolling the whole time for Ben.
Oh,
So
that's
unfortunately, but dude, I mean, he was pretty cool in the chat. He wasn't doing anything crazy, so we just left it alone.
Ben's awesome. He's
Yeah,
a good,
well, dude, I like Ben.
well, he's a good friend. So I don't know
Yeah.
who this dude is. Well, God bless him. I'm not sure says, I did see 4 textbooks on this site for free to download that probably would have some valuable info in them for a scientist anyways. It is a little too much math for my liking. Yeah, I'm not good with math. In fact, I had never done a fraction or algebra
Really?
like until I turned 52. Not a single day, not a single time, not once. Nope.
Really?
And I used to, when I was a data architect, I used to design financial software, but I never used algebra or fractions. So thank you, Crypto. I'm so glad to be back. You're awesome, man. But yeah, so what does that mean? I've kind of, because I'm dyslexic, I've kind of made up my own math that only works for me, and it always works. So it's pitiful.
Well, if it's building those coils, man, you definitely got it right. That's for sure.
Thank you. Yeah, I shy away from math in books just because I don't have the training.
I have to do fractions all the time, man. All my kids go, hey, come over here and hang our TV for us, or hey, come over here and do this for us, or fix this. You know what I mean?
Yeah,
So always have to do that kind of stuff, man.
that's true. That's true. You can't get away from math. I haven't done it conventionally. I mean, being a software engineer, self-taught infrastructure engineer, data architect, holding all these big titles meant that I can do a lot with computer systems and yet be a high school dropout. I think it kind of is similar. We all really aren't experts in the stuff that we're dabbling in, but we definitely have a really good perspective because we're not weighted down by preconceived notions. And I think that gives us an edge. We don't go in with, oh, that's already been done. It's already been done, nothing new here. That is the death of all creativity in what we're doing. And I don't know how many times people come up say, oh, that's already been done. Well, take your tiny mind and go to your tiny pond of ideas and be happy. I'm not gonna get on you.
Oh, Sean, I love that to hear that from you, man, because I feel the same way. You don't know how many people go out there and repeat the same physics garbage that I hear everywhere. And it's like, can you at least try? Like, let's do an experiment. Watch somebody do an experiment. Maybe have an original thought about it. Maybe flip the way you think about it just for that one time to see if something's different. Anything.
Right,
Nope.
right.
It's like, I won't say it, but yeah, they all the time. It's like when I hear, oh, everything's about magnetism, and I go, you do realize that if I take the frequency and shoot it sky high, there is no magnetism to it, right? I mean, you do realize that, right? So when everything's magnetism, what happens when I remove it? What happens if I invert the field and change it to radiant energy, and then you have no magnetism? I mean, if everything's magnetism, then what's the deal? Like, dude, I could throw a magnet in the air, it could float, everything else, if it was all magnetism, be easy, right?
Yeah.
There's no magnetic properties everywhere. It's all in radiant energy, and you have to flip a field to get it. It drives me absolutely insane to hear it. And then, yeah, anybody who thinks it's that, man, just, dude, go back to your little pond, like Shawn says, because you'll never understand what I do. So
That's good. That's a good point, because you get one-sided and you miss the whole other side. I'm learning that with Jarvis in electrodes, that there's this whole other universe of fields that have no magnetic properties. We're not using, when you have a field that's static, it has zero magnetic field properties.
yeah,
That's what
zero.
the electrodes are. There's zero magnetic properties. Now, one could say quantum, the quantum level, something is doing something, but I mean, there just isn't any evidence that there's a magnetic field at all. And so all of those fields you saw when I was running the glass up the side of the wall, those glass beads, there's zero magnetism. Zero. So that's what blew me away. That's a whole zero magnetism environment right there, right?
Yeah, but Shawn, the only thing that works all the way through the quantum level and scale up to where we are now, it's only resonance.
Yeah.
As a matter of fact, it works better in quantum than it does that we personally see when we build these things. Because a lot of people like always get it mixed up with vibration, and vibration's just slow. Okay, it's a slow form of resonance. It's not the same, and they always get mixed up in frequency. Does it go in? Does it amplify if they go together, or if you go one and then the next? You know what I mean? If they go in between each other, they just don't understand the resonance the same way. It's a tuning fork. It goes together, back and forth together.
Yeah.
That's what makes it so powerful.
Yeah.
It's that frequency together. They think it cancels it out. They think, oh my God, you have nothing. See, that's what you're looking for. I mean, if I build 6 resonant fields, right? If I start going coil inside a coil inside a coil inside a coil, right? You know that I'm looking for the smallest amount that'll fit in that little area in the Casimir effect. And I'm trying to shoot it out like a laser, but I'm going to amplify the living daylights out of it because they're all resonating together.
Right. Yeah. There's something about having every part, let's say, of a whole at their resonant frequency, because that's when you get an exponential, you get something exponential, something earth shattering. And it's always been in the back of my mind, because it's not an easy thing to do. But I don't want just my Tesla coil resonating. I want the physical copper wire resonating. I want the PLA plastic, the epoxy. I want their resonating frequency. I want complete resonance, and that's always in the back of my mind. I want to do that because how much effect is that going to be, that compound resonance? I mean, what do you think? Is it going to just shake apart and disintegrate, or do you think it's going to have some kind of power that we're not even familiar with?
I think that's a misunderstanding. I think it never breaks apart the material you're resonating, but it just keeps vibrating it. It keeps shaking it, right? But it does it on a level you're not visually going to see. You know what I mean? Like, you don't see your Tesla coil ever move. Mine never does. It
Right.
sits there and looks at me, right? But I know it's resonating. So
Right.
you go, okay, well, let's look at steel. How did Tesla take the earthquake machine and make it resonate steel? Well, it's just time and frequency. It took time for one area of the steel to get to resonate, then the next, and next, and next.
Yeah.
So you're spreading it all over the place by slow and steady, hitting that mark every time. Because the primary resonance frequencies are the low ones. You know, the 5 hertz, the 6 hertz, the 7, right?
Yeah.
Those are the primary ones. Then you get to the multiples, and then multiples into the kilohertz where we're at, right?
Right.
So we're not hitting every resonance frequency. We're doing this. This little field works here. We're jumping that way over to here.
Yeah.
Tesla knew to start it small and let it go and hit every single one of them along the way till it gets to the big one. I think that's what most people miss.
I think you're right. I think you're 100% right. So Crypto asks, any thoughts on this old man builds at Shawn Calderon? Oh, I can't see it right. Am I seeing that right?
I could show it on the screen, but I can't pull it up unless he puts it in private.
Oh, okay. Let's see what we got in chat.
Let me see. Hold on. Let me see if I can't find it on. He says it's a OWE one wire energy.
It's your one wire energy.
I don't know if it is or not. It's not showing up in my chat. That's right, because Bernie's on the other one. Yeah, you'll have to email it to me or something, Bernie, and we'll pull it up and take a look.
Yeah, I'm just scrolling through here.
Yeah, go ahead.
Yeah, Jabber, he says it's merely charge potential imploding in a longitudinal field, creating mass and gravity. A mass and gravity period, that's nothing more. Genetic Jabber always has really detailed descriptions. It really gets you thinking. So Time Energy says working with piezo as well, or piezo. Not sure, says they have made up this hypothesis world of stuff that is too small to see and based everything upon it. That sounds like quantum physics. They just sort of base everything on this in this world that's not intuitive. And I'm not. And it also, too, you see these big colliders, these particle colliders. What have they given us?
They're nothing. They're
We
junk.
put billions of dollars, and they promise to unlock the secrets of the cosmos only if you'll give them more money and give them a bigger collider.
Yeah.
They should be using those colliders for fusion energy or something that's gonna help the Earth. It's yeah. It shouldn't be
Yeah,
stuff.
those things are kind of a waste of time. They should rebuild Tesla's Wardenclyffe, and then you get somewhere.
Yeah. Somebody invest in that. Let's see here.
All right, Shawn, real quick. Here's the video.
Ooh. Interesting. Those are beautiful coils.
Yeah.
Is this from crypto?
Somebody pulled up I didn't read the name of the.
Look at this. Oh, wow.
Well, that's something different.
Yeah. Interesting. So
Well,
they're
hold
selling.
on. I don't know, but I'm going to pause it right there and go back to the. I don't know what the rest of that stuff is.
Yeah.
Let's go over to here. Maybe this is what he was talking about. This?
Yeah. I mean, I want to see under that table.
Oh, you don't have to. It's in the flashlight.
What's that?
That's a magnetic field.
The gold flashlight's a magnetic field?
Yeah.
I see. I thought there was something under the table.
No, those could be ball bearings or magnets, but they're just running in a magnetic field.
That's incredible.
I did this with a bunch of coils, especially geometry coils work this way. You see it going in circles?
Uh-huh.
Yeah, that's a piece of cake to handle.
Can you freeze it on that book on the left? Yeah, sorry. Right there on the left.
Energy medicine. Yeah, we're going to stay away from that.
Oh, I see. Yep. Okay.
Yeah.
That was a cool science book.
Is there anything under it? You don't need to. I got dollars to donuts says that flashlight right there is a big coil. And just like the geometry coils, it's running in a pattern. You know what I mean? You could put little geometry, and every point that it hits in the geometry, the ball circles. So it's like saying you hit here, 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 here. You know what I mean? Back all the way around.
Yeah.
And then it starts the thing, and it's like a merry-go-round. You just push, and then go by and push another area and push another area. Just like that. That's it. So I did that with every coil in my whole garage. I made magnetic spin. It was bifather coil, it didn't matter. Geometry coil, it didn't matter. Rodent coil, every single one of them. I took a number 1 coil from my Tesla coil and did it. It still rotates the magnets.
Have you seen a coil in the middle, like that flashlight, and then move things that are to the side of it? I mean, that's a fascinating magnetic field. I mean, it'd have to be powerful, wouldn't it? Because those points are 10, 12 inches away, right? The balls, I mean.
Well, that's quite a big coil, and it probably had a pretty big like core in it.
Makes sense.
Well, you know what? No, it couldn't have a big core in it. It had to be an air core. The core would have sucked in the energy.
Right.
Yeah, so it had to be an air core.
Yeah.
It had to be some kind of geometry deal.
Yeah.
And the outside's aluminum, so it's not going to give you much protection, if any. It's just going to blow right through that aluminum.
Right. Yeah, without getting into the wrong topic, I mean, life has frequency, energy, electricity. I mean, so to see that incorporated makes sense. That's probably all I can say without bringing up the H word.
So just so we all understand each other, the way that thing operates and the way that they were describing or showing it without saying too much is a geometry coil. You're not getting away from that. That's exactly what it is because of how it's operating.
Right.
So, but that, I mean, I'd love to tell you the whole truth about it. I just can't. YouTube won't let me.
And I know that minefield. We can't go in it.
Yeah.
So, yeah, thanks for sharing, Crypto. Beautiful coils. It's interesting how they're using them, and it was good marketing too to have a bunch of females in skimpy clothing using them. That had a bunch of old fat guys like me. They'd be like, "Yeah, no."
I need a whole new PR person now, Shawn. You gotta hire some hot chicks to sell my coils.
Subs will go up like triple.
Oh, I'm gonna tell him too. I'll tell my wife. Well, Shawn told me to do it.
Yeah,
He said
yeah.
it would sell really well.
A model comes out and carrying one of your coils, and this is $100, and you get this. No, oh boy, no, we can't go
He
there.
said we'll sell it on OnlyFans.
Yeah. So let's
Oh man.
um, got some more info. Yeah,
Oh.
charge potentials, capacitively imploding and longitudinal ether field, modality. That's what. Oh, that masses as well as gravity. I got to sit down and hang out with this Jabber guy. I mean, it's just that's a big.
Oh, he's got a whole thing going on. He did like 5 messages on it. I think he had to get a point across.
Yeah, he's.
Oh, it had nothing related to do with your work. He just had a point he wanted to say.
It would have found its way to my work. It has.
Eventually, at the very bottom.
Yeah. It still blows me away about the blue lightning bolts at the bottom and the yellow at the top. That just yeah, stuff like that. I just love to.
Oh, hold on. Blue at the bottom, white at the top, right?
Mhm.
Or yellow, like a
Yeah.
little off-white yellow type thing.
Mm-hmm.
The blue comes from the negative radiant energy. When you put the rod down the center, remember I told you when you touch it, it has a blue that comes off of it.
Mm-hmm.
Okay? So when you put that thing down the center and that pyramid being so short, you probably have this much of the rod in there,
Mm-hmm.
which means you definitely got a flip field underneath it. Okay, because you're getting the blue.
Mm-hmm.
And it would normally probably be white, but it's probably changing colors in the magnetics of it. Because you're right inside that field. You're not really going outside of the number 1 coil, right? Most Tesla coils are outside of it, so you'd get a yellow discharge.
Yeah, it's just incredible. The only other time we get that yellow discharge is if it's going straight to ground. That's another interesting thing because that number 1 coil is not going to ground. That number 1 coil is not connected to ground. The only thing connected to the ground is number 2 coil. That's it. And so
Yeah.
if you remember my other experiments that were connected to ground, it went yellow when it went straight to ground. But there's no ground in coil 1, right? Yet when the coil 2 strikes it, it's yellow like ground.
Well, that's what I mean. It's when you do high voltage, like DC flyback, right?
Mm-hmm.
It'll put off different colors based on the amount of amps you put into it.
Mm-hmm.
Sometimes I get pink, sometimes I get purple, sometimes I get yellow, I get white.
Right.
It goes through the whole color spectrum the whole way. I mean, because of the amount of amps. So it basically is trying to tell you that the amount of amps in there is the amount of heat, okay?
Mm-hmm.
Which means the magnetic field is that. So as you have it hitting the magnetic field, it creates the actual color of the light.
Mm.
That's why when you're out there and you're in radiant energy and you get to a planet, it has, you know what I mean, somewhat of a magnetic field. Any part that you can pull off that's magnetic, which may be very small,
Mm-hmm.
but it's still enough to create the light. Because the light's not there in the darkness.
Yeah.
It's only there around the planet. So, and it
Yeah.
doesn't have to pick up much. It just has to interact with it.
Right. That's interesting.
It's why no one understands field flipping, because they're not watching the color. They're not watching the fields. They're not seeing that that's a different field than this one here. You can't just say it's magnetism. It's a different field altogether. It's like when I tell you things rubbing together, right?
Mm-hmm.
Well, you don't think much about it until you're in your socks in the hallway and you're rubbing your socks in the hallway, and then you start shocking people.
Right.
Then you're going, well, what happened? Well, it's the friction that created the field with your body capacitance that gave it the voltage.
Yeah, that's what was going on in my experiments too. There's the friction and it created the fields that manipulated the glass. Really,
Mhm.
the glass was trying to work within the fields, and I know Joe mentioned that they had a hexagonal form in the earlier videos. And what I saw was, you know how you roll a dice and it has five. You roll a five on the dice. That seemed to be the shape that it was forming to me.
The one you were doing, the geometry in the little cup, we had the rod going down. It
Yeah.
kept forming a flower, the petals of a flower, like the flower of life. It
Oh,
was
really?
forming, yeah, it kept forming petals in there. And it would look like, oh man, not a daisy, like not a sunflower. It's got too many things on there, but like just like a five, leaf flower.
Yeah. I wonder if I can capture that real quick and we can slow mo it because I'm interested in seeing that.
Oh yeah, definitely there. We slow moed it when you sent it to me that one day. Yeah, pull it
Yeah,
up.
I can pull it up if you want, or you want to pull it up?
I don't have it right in front of me,
Okay,
Sean. You do.
here we go. I'm gonna share it here. 1 second. Let's see. Present. And what are we doing here? Here we go.
By the way, I think most of the chat would be into hiring the models for the coils.
Yeah, yeah. Let me know
They
when you
would,
can see.
they'd be of assistance. Yeah, it's up.
It's up. All right. Is this one you're referring to?
Yeah, hit pause a couple times and take a look at it.
Okay. Let's see. Let me move it back here. All right, let's see.
Oh yeah, you definitely see a flower in there. You can see it.
Yeah. You saw this. It's amazing. I don't see this. You exactly saw a flower. Look at those petals.
Yeah, that's a flower. Now
Wow.
I don't know what kind it is, but it definitely looks like a flower. Look at that one.
Yeah.
That's like a four-leaf clover almost.
Yeah, it does. That's
It's kind of cool.
incredible. Good catch. This is, there's no instruction book. I just love zapping things. I'm like you.
Oh yeah.
I think everybody in the chat loves electrocuting things. Look at these
So
flowers.
yeah, we got the right crowd, right?
I know, don't we? Don't we? Let's see in the comments here about the flower.
Yeah, I think everybody agrees that it was like a clover.
Yeah. Took
There's
those,
6 on some of them. Yeah, I saw 4 on some, 6 on another. Yeah.
yeah. Some of these flowers have to be a certain species. Because some of these have asymmetrical petals, but in the wild there are asymmetrical flowers. That definitely is a daisy. Or
Oh,
yeah,
look at that.
that's incredible. It's a little petri dish of glass and a little bit of voltage.
Do you know what the frequency was of that right there?
I want to say it's 185 kilohertz.
Hmm.
It's the wand. You know the wand that you use
Mm-hmm.
to shock your face? This is what it is.
185 kilohertz, huh?
Yeah,
Wow.
if you turn that zapper thing on and then
Uh-huh.
move your oscilloscope probe to it, you'll see the frequency.
Yeah, no, I've done that. I'm just looking at the flower. I'm like mesmerized by that. That's so
Sorry.
cool.
Yeah, I'm off topic. Sorry about that. It is cool. I can't get enough of it. Almost done here. I want to see if there's a poppy or that was kind of an orchid.
Yeah, because it's sparking out like one of those little plasma balls in the
Hmm.
center, and then it's lighting up the glass like a reflection or something. I don't know what you call it, but it's going through every one of them.
Right. And it's not supposed to go through glass. What is that? Glass is an
Well, I
instant.
don't know if it's going through it or if it's just, like I said, a reflection of the light. Like,
Oh,
because you could put, like, think about it this way: you put laser beam through a piece of glass, right?
mhm.
And it spreads out. You start getting different beams of different colors. Or if it's like a
Mm.
crystal like that, or you know what I mean, something like that, boom, it'll spread out. So think about it that way when you think about this. So the voltage must be going boom, 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 and the color
Yeah.
just like that, just kind of like a laser, which
Wow.
makes sense because as soon as you put high voltage in compression that it cannot spark over, you start to get a laser.
Mm. You can kind of see that action, that almost, because it's a real crisp light.
Mhm.
It's a sharp light, almost laser-like sometimes.
That's
Interesting.
what I love it when physicists say Casimir effect, and I'm just going, do you really understand what that means? Like, you know, you're creating a laser, right? Like, there's
Yeah.
no getting around that. You're forcing it together to create a
Yeah.
beam of light. Like,
Hmm.
I know you want it for propulsion, but God, man, think about it a little bit. You're going to end up putting your eyes out.
Oh yeah. Oh, I have a laser I bought some years ago, and it'll pop a balloon at 50 feet.
Yeah.
I have a under lock and key. It's more dangerous than firearms. You go blind in 1 second.
Oh yeah.
Yeah, pretty cool. So, all right. John says that's a coil and it is a wand.
Yeah. Just okay. Hold on. Jaren Visitor said Casimir effect.
Hmm.
Check this out. Take two flat pieces of aluminum. Okay, spray them both. Bunch of coatings. Okay, put the high voltage positive and negative on it, and then force them together.
Hmm.
At some point, a red laser will appear out of it, and it'll go straight back and forth, just like this, in the whole thing. So if you're in the wrong place when that goes off, you're
Yeah.
getting it. Yeah. So you're better off to go over there and find something to hold them and doing it.
Hmm.
But that's what I worry about when people just throw it out there. Oh, it's just a Casimir effect. We can make propulsion out of it. Well, let's learn how it works first. So
Hmm.
as you compress a field, you're compressing light in a magnetic field to make the light, right? We talked about the magnetic field.
Right.
Well, if you do it on aluminum, man, the magnetic field does not want to stay on that aluminum. So it
Right.
forces itself off the aluminum from the eddy current, and then boom, it creates that laser, and you're like, wow, dude, it'll shoot right across the room.
Is that from pressure? Are you saying you're squeezing the aluminum? And
Yeah,
then at a
you're
certain pressure, it emits a laser light?
yes,
Oh, interesting. And it's just aluminum, right? Being under high pressure.
yes.
Interesting.
Because of the eddy currents, you think it's this far apart, but the eddy currents make it like a pin. So it's changing the field on you, and you're not realizing it when you use different materials. So if you do the same thing with copper, copper just sucks it up, right?
Okay,
It,
yeah.
it it sucks it up and gives you kind of a repulsion on each one. You know what I mean?
Mm-hmm.
Aluminum doesn't work like that. It's totally different.
Right,
But
right.
if you use iron, they just clamp together. So
That's
yeah, you
true.
have to watch some of the materials you use.
Yeah.
So
I know
yeah,
aluminum has properties where if it forms an oxide on the surface, you can make it into a diode. Aluminum's in some interesting stuff. All right, so Society of High Sciences says, old man builds show. Sh- Shawn, my last two comments and see what he says. His last two comments and see what he says. Okay, that's one comment. Let's see, where is he? Here we go. This is the difference between the dielectric and magnetic 90 degrees out of phase. Society of High Sciences says look at the solar system top down, and you will see the magnitudes of the circular orbits. Look at it from the edge on, and you see a line that seems to terminate at 2 points in space. Boy, that was a tough one. I think he has more IQ points than me. Smart people.
Oh, I have a video for you, Shawn.
Okay. I'm just checking out the comments. You guys
Yeah,
are
yeah.
smart guys.
So this is an old video. So Boss sent it to me today.
Who sent it?
His YouTube is Boss.
BOSS?
What I'm going to do here is show you what's going on in the 3-coil system that I've posted in the video. I've received a new rear end restructuring out in some of the public forums by people that have no idea of what's going on in the world whatsoever except their own ego. But I want to take and show this to you. This piece of paper shows the cardinal points of how this coil is sitting on the bench in my lab. This is the north, east, west, and south. And there's nothing hooked to this coil at all. It's an L3 coil. If you followed my work at all, you know what an L3 is. If not, maybe you should check into the work. The spectrum analyzer, as you see here, I have it set for a span of 40 megahertz with a center frequency of 20 megahertz. And I'm going to go back to this coil, and I'm going to insert the probe, just this piece of coax with a tip on it, into the end of this coil. I got to move it this way a little bit.
One-handed camera work.
Yeah, old school.
I'm very well prepared, I can tell you. Okay, what I take and want to do now is show you what we're seeing on the spectrum analyzer. Not a whole lot, are we? In fact, nothing has really changed here that we can say has taken place. So we'll let this coil sit here for a minute. I'm going to take and back this. I want to move this back out of here a ways and let it just sit there for a couple of seconds, maybe 30 or 40, to where it will go into resonance at its spatial resonant frequency. Now, I know if you're a conventional thinker and you've been taught in the same universities I have, you're going to say, what is this idiot talking about? Well, there's a significant difference between self-resonant frequency and spatial resonant frequency. And I have a paper inscribed. It will be back on my website as soon as the hackers leave me alone and I find a new hosting service. But anyway, the paper will describe how you determine and how you measure the difference between self-resonant frequency and spatial resonant frequency. Okay, I think we've probably left this long enough now to where this coil now has established an oscillation on its own based upon the spatial resonant frequency of this coil. That SRF is determined by the number of turns, the size of the wire, the length of the coil, and the interwinding capacities of the coil itself. Now, this will vary significantly from a self-resonant frequency because you test and excite the coil for the spatial resonant frequency by only exciting one end of the coil from one end of your generator. So anyway, go out and look for those papers, look for those explanations, you'll understand what I'm talking about. So let's take a look at the spectrum analyzer and see if anything's going on here. Oh, lo and behold, we're now seeing something. If you notice right here, we have a very weak signal coming from the probe in that coil. Now, we didn't have that before, and I will assure you, I'll take and go ahead and move a marker over to it, that is the spatial resonant frequency of this coil. Let me go ahead and adjust the marker and bring it over. Okay, I've got the marker sitting right on top, and we're looking at the SRF of being 29.8 megahertz. And granted, we're minus 70 dBm down, but that's immaterial. We're going to take and demonstrate something a little better as we move along here. But you can see that this coil now is actually oscillating without anything connected to it. Now let me go down here, pull this wire out of the coil. Okay, it's free and clear. Let's go back up and look, and all we have here is the marker, which I'm moving around. There's no longer an oscillation taking place in that coil. Okay? All right, now I'm going to cut this into multiple video sections because we're going to do a number of things with this little coil for the demonstration. So this is going to be part 1 of SRF demo. Okay? Bye.
What do you think about that, Shawn?
Yeah, I'm trying to wrap my brain around that. It's amazing.
It was pulling resonance from somewhere.
Yeah. It's you know, we live around frequencies, we live around vibrations. So I mean, he's just drawing from that. I mean, we have an electrostatic field, the Earth's electrostatic field that moves. So I don't know why they call it static, because it's moving. But there's a lot going on with around us that we don't really think about. So I'd have to watch that video a couple times because there was some really cool stuff. And so he sent that to you? Is he are you just subscribed?
Oh no, like I said, Boss sent it to my email. He said, "Check this out. It was interesting," and yeah, it was. So I thought I'd bring it to you because you're like the resonance guy, man. You know what I mean?
Yeah,
This is like wicked, just out of nowhere. So we saw, just so we understand, that little pipe that they put around the internet. I don't know if you saw it. That they're supposedly pulling energy from, free energy pipe.
I haven't seen it.
Yeah, I have a feeling they're working on the exact same principle. It's just a simple resonance you're picking up inside the pipe. It's the same resonance he's picking up inside that. And he has the advantage of the coil.
Yeah.
And that coil being that short, that's what, 30, 40, 50 megahertz into the terahertz range. That thing is so small.
Tens of megahertz, easy. Mm-hmm.
Yeah, I wish it was in the regular hertz level, but that's not. So hertz level coil is huge. So
yeah.
Just to give you some perspective, at 32 gauge on a 4-inch pipe, just to get it into the hertz, not even the low hertz, you're looking at least 6 feet. 6 feet height. To put it in, say, 7 hertz or 8 hertz in a Tesla coil, you're looking at about at least 9 to 10 inches of diameter. Okay, at 32 gauge,
right?
Yeah, though the diameter of the pipe has to be that big, and it has to be at least 5 feet in order to get down to the very low hertz. At least that's just a starting point. That's just, let me throw something out there to see if it'll work. You'll know when a coil is in low hertz because it'll be massive. These little coils are in, sky high kilohertz, megahertz.
Right. I can't get the ZVS to run under 15 kilohertz. I just can't. I mean, I'm still trying, but yeah, I mean, John Bigman says miles of windings.
Yeah, it'd be huge.
You would need very thick wire, and yeah, I mean, it's something that I've always had in the back of my mind that I want to do, is I want to create these 1 to 5 hertz with high power outputs. None of this, how when the guy who drives by in your neighborhood and you hear this boom, 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 and it shakes your window cells.
Yeah.
I tell my wife, "Oh, I'm so thankful they're sharing their music with us." Uh, but they're playing with those low frequencies at high power, and they're not even in the hertz. Those are probably, I mean, they're not in the. They're probably still kilohertz. Probably still kilohertz. Maybe high hertz.
Mm.
Maybe 800 hertz or something. They're definitely not 6 hertz. I'm sorry, they're 90 hertz or 100 hertz. They're in that probably range of under 1,000. But yeah, to dial that down to 1 or 2 hertz with high power, yeah, that's always intrigued me. Every time I go to the thrift store, I buy the giant woofers they sell for $3. They're trying to get rid of them, and I have 5 of them in my garage because I want to see if I can hit those low frequencies with a lot of power.
Mm.
So they always attract me because there's a lot of power in those lower frequencies as far as moving the everything around you. If you want to affect everything around you, you hit those frequencies because it goes through everything.
Hmm.
So yeah. Let's see, we got here. Gold Godheart Guardian says, I want to rebuild these antennas with high altitude weather balloons and create a wireless network. Huh. See, Stefan G says, I hate Starlink. Yeah, at my cottage in the no man's land in Wisconsin, I have to have Starlink. It's that
No,
or no internet. No phone, no internet.
have you used Starlink there? Is that what you're saying?
Brilliant. It's way faster than here in the city, and the city has the fastest internet.
Mm.
Starlink is gold, pure gold. The network speed is so fast you think your stuff is broken because when you touch something, it comes up so fast. You go, "Did I even click?" It's like
Wow.
it's super fast, and it's not cheap. Sorry, it wasn't that expensive. I think it was $500 to get it set up, and it's something like $150 a month, which is high. But if you want internet in the woods, and it's the best internet, it's awesome.
Kind of has to do what you got to do, huh?
Yeah, exactly. And because there's no light noise, because it's literally 100 miles in the middle of nothing, forests, you can see the Starlink satellites and a perfect stream come right over our cottage over the lake. A perfect line of stars, all
Nice.
stars, and they cone right over the sky over our cottage. It's really bizarre. Um, he has so many of them.
Yeah.
Jabber says it's horrible ruining my star view. Yeah, it is weird with all the beautiful stars and planets, and all of a sudden you have this string of satellites. It makes sense, I guess. See,
Oh man, that's funny.
yeah, they're just having some good talks here. Uh, Ian Jackson says, worth noting that when lights went out in Spain, the frequency moved to between 8 and 13 kilohertz, it says X hertz, and 12.5 is the quarter wave harmonic of the grid frequency.
Hmm. Interesting.
Yeah, Stefan says sky pollution, like we don't have enough already. Yeah, I mean, there's plenty of stars, okay? It's a pretty big universe, but it is weird. And I'll tell you a story. So my wife and I were laying out on our dock on the lake, and it's so dark you can't see your hand in front of your face.
Okay.
Yeah. And we're looking at the stars, and I'm like, oh, honey, look, there's a North Star, and oh, look, that's Venus. And then this line of marching lights came. This is before I heard of Starlink. And I looked at my wife, I said, these are UFOs. Because I've looked at the sky forever. And I was freaked out. And I ran upstairs, grabbed my phone, and I Googled it. and it was Starlink. Because they look otherworldly. They do not look like they belong in the sky. They, oh my goodness, it's terrible.
Oh, he's creating UFOs. That's great.
My heart was racing. I gotta film this. Let's see. No, just some comments. Lots of nice things. Wow, we've been here 2 hours. I'm having a really good time. I really appreciate you having me on, Nathan. It's I'm glad that some of the stuff I had was interesting to you. So what do you think about electrodes and some of the experiments?
Dude, hold on a second. Oh, there we go. Yeah, I think you're doing really well with it. I keep looking at that stuff, and it looks like you're putting a lot of heat into it in order to flip the field, right?
You know, I mean, in the plastics I do, but in the friction stuff, it's no heat. I mean, it's literally, even in the friction, so that black tire rubber behind the bowl, it's not touching the bowl. Its field is crossing through the plastic bowl and hitting the glass, and the glass's field is passing through the yellow plastic bowl and hitting the rubber, because there's no friction, no touch. So it's just a crossing of fields that we don't think about.
Yeah, my concern was if you put too much heat into it, you're getting too much magnetism in it. And then as soon as you want to catch it and stop the process so that it holds the field, as soon as you heat up a liquid to go in there, or if it has a chemical effect that creates heat, it's going to throw off the field you were looking to create. It has to be like a cold pour, fast set to hold that electric, right? You know what I mean?
Yeah.
And it'd be better if it was like a liquid material that just hardened quickly, or that it'll harden in the process of putting the voltage through it. But then you have to run that thing at such a high voltage to meet out as many amps as you possibly can to hold that field.
Yeah.
So,
yeah,
I mean, it looks challenging, man. I don't know exactly how to set it up. I mean, charging things looks fairly easy to charge it. To continuously hold the charge, it seems a lot different.
That's exactly right. It's because charge leaks. So if you pull your sock out of the dryer and it's making that staticky sound, and you pull it, put it on your foot, then it's leaked already. It's leaked out into the carpet, it's leaked out into the air. So you don't have that static electricity that it had in your dryer, clothing dryer. So to stop the leakage, that's the key, because you could put a liquid on there to harden to keep those fields in place, but that liquid might take your charge away. That's the thing, is you have to play the charge game. And that's why the glass was saying there's something on the other side of this bowl that has what I want. And then the outside of the bowl, the rubber's saying I have something in that bowl that I want. And that's fascinating to me. It's just to hold it is what you're saying is the challenge.
Well, okay, so it has to be molten, okay, or just in a liquid state that has to harden real quick, right?
Yep.
So the more material that's not charged may cause a problem. So what's a cold process that'll hold it? Because it has to be that. It can't be a hot process. It won't work. Because you can continuously keep running the charge through it as long as the material sets. You know what I mean? Then it will continue to hold charge, because that looks like the only way Plasma Channel achieved it is he had to continuously put it in while it was setting.
Yeah. Yeah. The thing that he doesn't show you in the Plasma Channel is how well he's held that charge a month later. And I've built higher charge electrodes than his. where you could feel it at 3 or 4 feet. And yet I go the next day and that charge is half. And then the next day it's lower. And a month later it's something, but and then there's so many factors. All I did is give you little snippets. And I know you know that because you know a lot about what I'm doing, a lot about fields. But I just wanted to highlight that it's this strange environment where our fields, if you get the right materials, the fields are gonna interact with each other um, without touching each other. That's the big thing that interested me the most.
So let me ask you this, Shawn. Have you ever had a spark gap or a circuit cool down on you? Like it's running at 240 degrees on the spark gap, and then all of a sudden it'll run at room temperature.
With a spark gap, I haven't. I know when I'm in perfect resonance, my transistors, my MOSFETs, they're perfectly cool and there's no heat in my system and the sound is not loud when I'm getting all that plasma. I know that sweet spot. And it always surprises me because I'm pulling out these 6-inch, 10-inch sparks, and yet everything's cool and it's quiet. But I've not experienced it in the way that you're saying.
Okay, so when you do that, your circuit itself is in perfect resonance. Okay, and the spark gap is in resonance with the circuit. So it's almost like you have to run a coil on each side of it, put it in resonance in between it as the spark, and let it charge like that so that the heat is far less. It's room temperature. But then any liquid can set perfectly in that. You know what I mean? Because there's no extra heat, so there's no loss on it when it cools down because you're not overheating it.
That's interesting theory. That is real interesting.
So it would be something to look into.
Yeah.
I've seen it in several systems. I've seen it in my system. If it's oscillating properly, there's no impingement, there's no clogging. I don't know what you want to say the best word is, but it's not there. It doesn't slow it down at all. You get free flow in electrons. You know what I mean? Or I should say this. I always see electrons as the impedance. So just hear me out. And this is kind of a wild thing. So woo, here we go. Okay? Electrons to me are the impedance. They're what creates your magnetic field. They're what slows down the electricity itself from free flowing. Okay? They're clogging the artery in there, and they're slowing this thing down and creating the magnetic field. Right. We look at it as a great thing because it creates a magnetic field, but the buildup of an electron is basically it forms a little ball, puts in static electricity, and creates heat. And that's what it continuously does. So I always look at the electron as something that comes in and creates a magnetic field, but then when you run it in cold energy, it takes that out. It removes that electron so there's no buildup in it, doesn't clog anything, and it's a free flow of electricity at a very cold temperature. That's how I see it. So when I look at this, I say, okay, we need an electric, put it in cold, make sure that you get the spark to go over so that the electricity is very high, but the magnetism is nothing. Okay, we don't want a buildup of a field on there. We don't want any clogging. We want it to go straight through.
Yeah.
The faster it goes, the better, because that means it's charging way more in an electric than it ever would, because we're not trying to make a magnet.
Exactly.
So that's just my idea on it. It's a little bit different than everybody else's because they think electrons are everywhere. I see them like little Evos that are sitting on the end of your wire, and they'll just break out in plasma. You know what I mean? But that's not what you want on this. You want this thing to flow fast.
Plasmas works against you. You have to have a strong field. No plasma. I do the redneck trick where I dial in the high voltage and I put my ear next to the electret, and then I dial it back until any sound is stopped, And then I know that there's no plasma leaking. It's straight field. And because, yeah, it's interesting. The thing about electrodes too is that airflow takes your charge away. Something as simple as air. So when you're talking about this cool liquid that isolates it right away, I mean, you have to have all these factors controlled. I have two vacuum chambers, and I have a clear one, and then I have a big, looks like a soup pot. I'm thinking about moving it to the vacuum chamber, so that way I don't have the air problem. I have no way to leak it, and then come up. I mean, I have ideas of what you're saying. What's a cool thing that can lock in that field right away without loss? So I appreciate that. You give me some good ideas. The guy with the coil and the probe, the spectrum analyzer, I'm gonna try that. Just
Yeah.
get it. It's cool though.
It seemed like a pretty straightforward test, right?
Yeah, it did. It's amazing. Awesome stuff.
Well, I think, son, even if you take a like a ball jar,
Yep.
drill a hole in the bottom, okay? Put your anode and cathode in, so they're here. Now put your electrodes in the center and charge it. So predetermine your shape when you do it, and have it sitting in there like a capacitor, and see if you can't get it to go. There's only so much air in there, and if you pull a little bit out, you'll probably have it. It doesn't take much.
Say that again. You said put it in a pipe?
Like a ball jar.
Ball jar. A ball.
Yeah, like drill out the bottom so it has a hole in it. Kind of like you see a lot of plasma experiments. You know how they drill out the bottom, and in the cap they put in the thing for the suction? Yeah. And do that. Make it into an anode and cathode, preset your electrode in there in like a molten level. So like however long it's going to take to set, I would even try resin and just get the resin in there. You know what I mean? And mix it up with all, you know what I mean? And just hit it and just let it set under just a tiny bit of pressure. I bet you'd pull through faster.
Yeah, I'm writing that down. Good ideas.
And then use that circuit that I was telling you. You can take a frequency generator and then take a trigger circuit, man. Put in whatever frequency you want. It'll override everything in that ZVS and a flyback.
Yeah.
It'll do it real fast, man. Or you can do it to a straight coil if you wanted to get down to the hertz, because to make a rodent coil spin a magnet, you just put in a DC pulse and put it at 7.85 hertz. And the round magnet sphere will spin all day.
Yeah, I think Ben showed us that. I'm just trying to wrap my head around this too, though. A lot to chew on.
You just got to find that perfect material. That's the hard part.
Yeah, exactly. Yes. And there's not a lot on this field. And people go, oh, no, we have Tang. What is it? Tribo Electric Nano Generator, TENG, Tang. They've done a lot of research where they'll make a sidewalk. And if you walk across the sidewalk, you're generating power. Here we go. Plug in a vacuum chamber, resonate 2 probes that go down 22 plates that are separated by microns. I think he's talking along the same lines as you were saying.
Yeah, I think he is.
I think he's working along those lines. It's a bummer to charge something and then watch it dissipate because you can't lock it in. And this is where Jarvis has been really my mentor in electrostatics, because he's been studying this for 20 years. And so I'll run some experiments, run it by him, and then he gives some really good feedback. But I really like how you're thinking, because it kind of zooms me out. You know, you get too close to a problem, and then someone goes, no, step back, look at it differently.
You want to eliminate the spark. I'm sorry, I forgot all about this, Shawn. You want to eliminate that spark. You want heavy statics, you got to eliminate the spark.
You can't have it. You
I,
need.
I've been looking at your experiments, just mesmerized by the plasma that I'm seeing in the colors, and I'm not even thinking, no. Static electricity, you got to eliminate that spark.
Yeah.
There's no getting around that. So
Yep.
you take a container and you put the like a bigger size on one side, just aluminum foil, and smaller on the other. It'll create a nice static field in one direction throughout the entire thing. It'll pull the small to the big, and it'll push a flow in that one direction. Put two DC flybacks in series, put it on that frequency generator that I'm telling you, make a perfect static voltage set that'll stay for a long time.
Yeah.
Take your material, put it in there, and allow it to set. If it takes 6 hours, then it takes 6 hours, but this thing will hold that long. I did a static electricity experiment with paper to move it up and down a little thing,
Yeah.
but it's the same principle. It had a big plate and a small plate, and it made it go in one direction, and it had no sparks whatsoever, but
Yeah.
that static would charge the living daylights out of the material in between.
Yeah. Yeah. All very good ideas. I've been wanting to switch to flyback setup because I want that high voltage. I want the rippling DC. I don't want the straight DC. That makes sense. But I don't want sparks. Sparks are bad. But to have a little bit of ripple in it to kind of jar the atoms, kind of get them to give up their stuff and get their fields all aligned. And I wanted to show you. It wasn't my presentation, but I think I skipped it. But I wanted to show you my flyback setup.
Oh yeah, let's take a look.
Yeah, if I can find it.
I'm telling you, Shawn, that circle changed your entire view of it.
Yeah, when are you gonna do a video on it? Because I want to watch it.
I'll do it, man. I'll do it right away. I have the circuit. I bought a bunch of more parts for it.
Because I'm gonna say Ian needs it for his stuff. I need it for my stuff. So that's two people that need it. So I mean,
You know, the circuit came off of my gravity flyer. I had to find a way to change the frequency and hold the frequency for a very long time.
crazy.
Yeah, and it was 18 volts, 2.5 amps is what the power was to go into it. The two DC flybacks thinned it out so much it came out pure static.
Wow.
And at a distance of about this far, so about 6 to 8 inches at least, I could get a massive static field out of it.
Wow. That's it. So really, in effect, you were getting the potent field, a dense, straight static field.
Yes.
And that's what's really hard to do.
That's what you want in your electric.
Yep. Oh yeah. The better. In fact, one of our goals I think we talked about is to have a coulomb of charge, which is an obscene amount of charge, and to hold it in an electret. That's crazy cool, crazy hard, crazy tough. But that's a high goal.
So real quick, Dennis said ion wind. It's the stage in any DC flyback before you get the hiss. That's the static field. As soon as you get the hiss, it's game over. You've already failed.
Yeah.
Then because when that hiss goes, you got plasma. That's that ion, right? You don't want that. You want right before that, which is the static field. That's what you want, and you want it as from one point to the next, and it has to do with the size of plates.
And if you're getting the hiss, you're moving air ions, and if you're moving air ions, they're stealing away your field.
That's the air you're having problems with.
Leaking. It's really, I can get it where it doesn't have ion wind. I can get it the field nice. It's just then now how do you lock it in? How do you now pour that liquid, if you like you said, to hold it? That's the step that is probably one of the hardest.
Well, if all it is a circuit that you need to hold it, I'll get you the circuit. And then if you got the material that'll do it while it sets.
It's the material that holds it that I haven't figured out yet. It's not the field. I wanted to show you, I can't find it, but my setup is 6 flybacks. It's a setup that is pretty awesome for that field.
Those
But
are big ones you got from that TV, that projection?
no, it's you can buy it. Oh boy, why don't I have it? Let's see. I thought I sent it to you in Messenger, but maybe I didn't. But it's a big box. Let's see here. It's about this size, and it's has 6 flybacks in it, and it's used to electrify paint. So when you're using the paint sprayers, it puts a little charge on the paint, so the paint goes on thin and evenly distributed. And they use it for painting cars, and it's basically a painter's thing. But since it's made to put a lot of static electricity on paint molecules, why can't I use it to put a lot of charge on my particles, whatever particles I want to use? And I was doing that with the glass. And I'm doing it with the glass, which is the macro, because the glass beads are too big. I need to be doing powders. I need to be doing things minute. That way I can get every single fragment charged, if that makes sense.
Mm-hmm.
So, but playing with the glass spheres lets me see visually what I should be doing at the powder level. So that's why I'm playing with the beads, because at least, oh, I can do the beads this way. Now I can take it to the next level and go to powders, nano powders. And so that's my thinking. But I like where you're going with that. Again, that cold freeze lock of the field. I just have to think about that for a lot. I think I have to think about that. And I'm so bummed I can't show it to you. I don't know what I did with it. Well, Nathan, it has been a blast. And I appreciate you having me on your channel. I really do. It's a high point of my month. And I appreciate it. I appreciate all you guys listening to me blabber on for 2 hours and 20 minutes.
John, they love when you're on the channel, bro. Don't even worry about that.
Appreciate it. You guys are too good to me. All right. Well, I copied these comments into a folder, so I'll try to skim through them, guys. Sorry we didn't get to all of them. You guys always have good stuff, but I appreciate you guys hanging in there with me. And I hope you didn't miss the starting of it, because we had some good stuff. But it's great to see you guys. John, Joe, Negrez, Jason, the box, Elijah Tack, Jason, Straight Dope, Joe. That's Joe. Oh boy, guys, I don't want to miss any of you. Brandon, Coates, Dennis, Yanni. Good guys. If I didn't say your name, I'm sorry. Crypto, you're the man. All right. Nathan, I'm gonna have to head out, good sir.
Shawn, thank you very much, man. I do appreciate it, man. Guys, chat, you're awesome. This has been cool, man. I missed you, man. We're gonna have to get together here in the next couple of days and figure some stuff out, and I get you that circuit. But yeah, awesome presentation, man. Very good.
Thank you so much. Good having me, guys, or good having you guys. Thank you so much.
All right, let me pull this up.
Your cool ending.
Oh yeah, watch this, because you're gonna see Joe's crystals he pulled up.
Awesome, can't wait.
The old man will. The old man will. The old man builds. The old man builds. The old man builds is broken in the head. People not seeing reality has put them in the red. Where conscious and spirituality restricted from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds.